today's lecture, we will discuss about the idle speed control. The operation of an automotive engine at idle involves a special consideration. Under idle condition, there is no input to the throttle from the driver via the accelerator pedal. The engine must produce exactly the torque required to balance all applied load torques from the transmission and any accessories such as internal friction and pumping torques in order to run at a steady idle angular speed. Certain low torques occur as a result of driver action. For example, change in the transmission selector from park or neutral to drive or reverse, as well as switching electrical loads. However, certain other low torques occur without a direct driver command. Example, air conditioner clutch actuation. As in all engine operating modes, the torque produced by the engine at idle is determined by the mass flow rate of intake air. The electronic fuel control regulates fuel flow to maintain stoichiometry as long as the engine is fully warmed, and may briefly regulate fuel to somewhat richer than stoichiometry during cold starts. Normally, the electronic engine control is intended to operate the engine at a fixed RPM regardless of load. It does this by regulating mass airflow with the throttle command from the driver at 0. The airflow required to maintain the desired idle RPM must enter the engine via the throttle assembly with the throttle at a small but non-zero angle. Alternatively, some engines are equipped with a special air passage that bypasses the throttle plate. The idle speed control mode is used to prevent engine stall during idle. The goal is to allow the engine to idle at as low an RPM as possible, yet keeping the engine from running rough and stalling when proper consuming accessories such as air conditioning compressors and alternators turn on. The control mode selection logic switches to idle speed control when the throttle angle reaches its 0 position and engine RPM falls below a minimum value. Idle speed is controlled by using an electronically controlled throttle bypass valve, which allows air to flow around the throttle plate and produces the same effect as if the throttle had been slightly open, such that sufficient mass air flows to maintain engine operation. There are various schemes for operating a valve to introduce bypass air for idle control. One relatively common method for controlling the idle speed bypass air uses a special type of motor called a stepper motor. One stepper motor configuration consists of a rotor with permanent magnet and two sets of windings in the stator that are powered by a separate driver circuit. Such a motor can be operated in either direction by supplying pulses in the proper phase to the windings. This is advantageous for idle speed control since the controller can very precisely position the idle bypass valve by sending proper number of pulses of the correct phasing. A digital engine control computer can precisely determine the position of the valve in a number of ways. In one way, the computer can send sufficient pulses to close completely the valve when the ignition is first switched on. Then it can open pulses to a specified known position. In addition, the digital engine control system receives digital on or off status inputs from several power consuming devices attached to the engine, such as the air conditioner clutch switch, park neutral switch, and battery charge indicator. These inputs indicate the load that is applied to the engine during idle. Coming to the acceleration and deceleration, during hard acceleration or heavy engine load, the control mode selection logic chooses a scheme that provides a rich air fuel mixture for the duration of the acceleration or heavy load. This scheme has the capability to provide maximum torque, but depending upon driver demand, suboptimal emissions control, and relatively poor fuel economy regulation. After the need for enrichment has passed, control is returned to either open loop or closed loop mode depending on the control mode logic conditions that exist at that time. During periods of deceleration, the air-fuel ratio might be increased to reduce emissions of hydrocarbon and carbon monoxide due to unburned excess fuel. However, enlightenment is limited to an air fuel that avoids excess nitric oxide production. This is a complete control diagram shown through which acceleration and deceleration can be achieved. In this mode, the engine speed is controlled to reduce engine roughness and stalling that might occur because the idle load has changed due to air conditioner, compressor operation, alternator operation, or gear shift positioning from park neutral to drive. Although stoichiometry mixture is used if the engine is warm. In the upcoming lecture, we'll start with the engine cranking.